Unfortunately, when we start talking about mobile routing, we hit kind of a big problem. And that problem is an IP address is assigned on the assumption that the host, this guy's a host at the end here, that the host will stay connected to the same subnet. Throughout a session. So I'm using session loosely here. Basically by session I mean from turning on the device to turning off the device. So to do any particular task, that's what I mean by session. And as I said, that allows us to hierarchically organize the internet. So if I agree that this guy will always stay connected here and will never change, then I know that I can easily assign this number. So I know that he'll always stay connected to 130.63.96, so no problem. The problem comes here. If let's say this is 130.63.97, and this guy is now mobile, he ends up over here. So in this case, hierarchical routing no longer works. If this guy keeps his same IP address, his packet will get routed here and we'll never reach him. So that's the problem. So this assumption of being constantly in the same subnet is violated in mobile networks. So in some sense, we could solve this problem by wiping out this subnet. So in other words, if I agreed that everybody in 130.63 could move around from subnet to subnet, then we could basically consider this all part of the same subnet. And these we wouldn't call this fixed routing. Maybe this would be some kind of virtual Ethernet or something like that, and packets would bounce around in here. But any packet destined for 130.63 would end up here, and then would be somehow routed internally so as to arrive at the same destination. So the problem with that is that where do you stop? So you could expand that to here. So let's say we're now not talking about yorku.ca, but we're talking about cell phone providers. And let's say you're walking around with your cell phone, and you cross a roaming boundary between, let's say, the Bell network and the TELUS network. So there's no guarantee that both Bell and TELUS will be in the same subnet.
So can we have like multiple routers with the access points, like multiple access points with same IP, or maybe same SSID?
So no, IP addresses still need to be unique. This problem is actually, eventually we're going to solve this problem by assigning each device two IP addresses. One that's fixed and one that's dynamic. My point by doing this is that eventually, if you insisted that everybody had to have one single unique IP address, it would eventually, the hierarchical structure of the internet would break down, and everyone would need to maintain the entire routing table, the entire internet, which is simply not possible.
So you can have two IP addresses.
You can have this guy can have two IP addresses.
So two people have the same IP address.
That
They're
is
in
not
different countries.
That is not allowed. It's not allowed to have. Okay, so for one thing, think about how that would happen. So here I am in Canada.
Because the main person assigns the IP addresses for each router.
That's right. Is there a question over here?
Do you need to have two interfaces?
Say again.
Do you need to have two interfaces for more than one IP address?
What we're going to find is that this guy has just one interface, and there's a virtual interface somewhere else that keeps track of where he is.
So we have a problem over here. Like, can we, the way you said at your router, it becomes a subnet.
Yes.
So can we have a structure like a tree structure of the system, so it can actually tell somehow that the destination has moved from that router to this router, and we just inform it to the York router. It will just know that it's right now in the different.
In fact, that's exactly the right idea. So what will happen is the packet will get here. We'll call this guy the home router. The packet will get here, and this guy will realize, oh, that guy actually moved to the following subnet that I'm keeping track of, and then the packet is forwarded. So yeah, that's exactly the right idea. But okay, so here's figure 2, which is what happens when we have mobility. Figure 2. So over here we have a source, let's say, and a destination, IP address 1.2.3.4. So normally, this packet would be sent to the 1.star domain. But then thanks to mobility, so he starts out over here, thanks to mobility, ends up over here, connected to the 2.star domain. But he still has the IP address 1.2.3.4. So his packets get sent down this road. But if he's actually attached down here, he will never see those packets. Those packets will be lost forever. So you might think, okay, how many internet devices could there possibly be? Maybe we could have a case where everyone could keep the entire routing table of the entire internet. How hard would that be? So firstly, how many IPv4 addresses are there out there? Yes?
Just 4.2 billion.
4.2 billion, sounds about right. Okay, now think, yeah, so actually, what is it? So we have 2 to the 8th, 2 to the 8th, 2 to the 8th, 2 to the 8th, which is 2 to the 32. 2 to the 30 is about 1 billion. So 2 to the 30 times 2 to the 2 is about 4 billion. So you're right. So if we did that, okay, so 4 billion, right? I mean, computers have big hard drives these days. Could possibly do that. But think about how often these things will change. Every time somebody moves to a different subnet, or every time somebody does something, you'll have to completely rebuild the entire routing table and send it to the entire internet. So that's clearly impossible. So basically, every thousandth of a second, you'd have to broadcast 4 gigabytes to the entire internet, and that's not going to happen. Okay, so the idea we're going to do, the solution that we're going to pursue is the following. I mean, this doesn't work. It does not work that this guy could have this IP address and be connected to that router, because this router is the 2.star router, and his address is 1.2.3.4. So that's a basic violation of the main principles of IP.